So in the last topic, we just got you started understanding floating point, the real number data representation. We took the real numbers, which are in a decimal format, the base 10 format, and we converted it over, mapped it over into a binary representation of that same data. We were able to deal with the negative sign as well as the decimal point, right? What you need to be aware of is floating points can be approximations. This can get you into trouble. So you want to be aware of this. Now, let's understand why. Infinite repeating patterns. Computers do not know how to deal with infinite repeating patterns. There are only so many bits. We saw that before, right? We saw that in a 32-bit machine, there were 23 bits available for the integer. In a 64-bit machine, there were how many? Well, let's go back and take a look. There were 52 bits available for us in a 64-bit machine. Do you see this? Here's the 23, and here's the 52. Also look at the exponent of what we have. We have 8 bits, and we have 11 bits. We have a limited number of bits available due to the architecture and the constraints of the machine that we're working with. So if you think about a repeating number, all right, let me give you an example. So here's 1/6. And if I convert that over into a decimal point notation, we're used to seeing it like this, correct? So you can say that it's 0.1666666, and then we'll just put this line over the top. And in our mind, we're just used to knowing as humans that, okay, that's a repeating number. It will continue forever, those sixes. However, in a computer, we're limited by the number of bits that we have. Therefore, what it's going to do is it's going to go through a rounding process. And that's due to the limited number of bits. So therefore, what the computer will represent it as is this. Notice that it rounded it at the end and put a 7 onto the end. This may not seem significant to you. However, if you're trying to work in a system that needs to be extremely precise, such as the financial world, and even in the engineering world with instrumentation, these little indiscrepancies might get you. For the most part, they're not going to be a worry for you. You just need to be aware of them. In PHP, it takes care of it for you. In some languages, and a lot of languages, it does not. So therefore, when you're dealing with financial numbers, you need to be aware that this system will give you unexpected results. So let me give you an example. I'm going to switch over and show you some code. All right, so I wrote some code here for you. And I'm just going to show you one example in code of how this can get you in trouble. So what I have, this is PHP, by the way. I have a variable that I've defined as $approximation, and I'm setting that equal to, so I'm making an assignment. I'm doing an addition problem here. I'm taking 0.1 plus 0.2, and I'm storing the result here in my variable that's $approximation. Then what I'm going to do is I'm going to put it through an if. And I'm going to say if the value that I've stored in approximation equals 0.3, because our mind says, well, yeah, 0.1 plus 0.2 is 0.3, right? So therefore, this should equal, and it should come back and echo out, yes, these are equal, silly. Else, it's going to say, no, they're not equal. What do you think it's going to do? Come on, what do you think it's going to do? If you're not sure, why don't you just stop and go ahead and do this yourself? Spin up desktop server and run it yourself. See what happens. You're going to be surprised. Ready? They're not equal. All right, so let's take a look at why. Now, PHP takes care of this for us. So instead, we've got to switch over to the console. So here in the console, let's go ahead and try that. So I'm going to take, and let's add these together. I'm going to take 0.1 plus 0.2 and add it together and watch the result that I get. Do you see that? It comes out to 0.3, a whole bunch of zeros, and then a 4 at the end. Oh, okay. And that is because if you look at how the numbers are converted from base 10, our decimal numbering system, we don't have a reference in there for the 10th position. Therefore, our number accuracy in binary is a different set of numbers. It's not going to always be precise, and this is one of those examples. It's not precise, is it? So let me walk you back through that. So our approximation, this was the code that I gave you, right? And you would think in your mind that, well, it's 0.1 plus 0.2 is 0.3. But when it outputs it, it gave us a no, they're not equal. So 0.1, this is the binary representation. There isn't an exact because it has a repeating pattern. Ready? This is the repeating pattern. Notice it. What do you see? 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. And it's just going to continue on forever. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. So we're going to get an accuracy right there. All right, let's do the same thing with 0.2. And you'll see the repeating pattern. Do you see it? All that it did was add a 1 onto the front, the most significant bit. But the rest of it is repeating. So if I go and I add those numbers together, the computer gives me back this number. It's not exactly 0.3. The repeating patterns are rounded. The result is from that rounding. It's just an approximation at that point. So therefore, if you're trying to work with decimal point numbers, no matter what language it's in, you need to be aware if you're trying to compare two numbers. They may not exactly equal what you think they should. All right. I'm going to deal with something a little bit different now. So I've showed you the inaccuracies in knowing that it's just an approximation with floating point numbers. Now, I've been showing you multiple different representations of data, right? I showed you how it went from decimal system, our counting of 10 digits, and converted that over into binary. And then I showed you how to take a signed integer, so a negative, and how we would map that into another representation in binary. And now I just showed you the real numbers in that representation in binary. How does a computer know which bit mapping to use? Are you wondering that? Are you getting kind of confused? So if we look at all these numbers, how does it know which one is being used? Well, let me tell you, the way it knows it is because in the software that you're using, depending upon what language you're using, it's telling it which numbering system to use and which addition to use. So that when it gets broken down into that machine code, it says, I'm doing floating point math. I'm doing signed integer math. It knows what it's working with because the software is telling it which mapping to use. I just wanted to be clear because I know you might be sitting there right now and wondering, well, I've got all these representations. Which one does the computer know how to use? It's because you're telling it. Therefore, when you're working in a numbering system, in the data representation, you notice that there's different types of representation available to you, and it has X number of bits to it, a different size of memory available to it. And when you start using those in that language, the language itself knows how to break that down. And that bytecode, for example, in PHP breaks it all the way down into the instruction and says, hey, I'm doing floating point math. Oh, I'm just doing whole number integer math. Nope, I'm doing signed integer math. It knows. So let's do some takeaways. Computers use scientific notation for floating point. The size of the machine that you're working on, or the size of the machine that is hosting the website, right, determines the precision. The bit pattern is a group of bits for the three major components, which is the sign, the exponent, which what is that? That's the position of the decimal point before we converted it. So where is it located at? That's the exponent and the mantissa, or the significand. 3 elements that we've captured in our new bit pattern. Repeating patterns are rounded. Therefore, approximation can occur.